the next presentation, we're going to go ahead and look at an alternative method to programming with PowerMill. Most people are aware that PowerMill can drive your expensive 3-axis and 5-axis mills, but are unaware that PowerMill can also program industrial robots using the same type of programming flow as you would when you're programming on those mills. So today we're lucky enough to invite in Aaron Kinnett from Autodesk. Aaron has a wealth of knowledge in manufacturing and is an expert on this subject matter. So I'm sure there'll be some questions that are generated throughout this live event. After Aaron is done, we'll go hang back and answer them for you. So feel free to submit them throughout the presentation on the right-hand side of your panel and upvote them as if you feel that some of the questions deserve response quicker than the others. So with that, I'm going to go ahead and bring Aaron in, and you can take over.
Good afternoon, everyone. Thanks for joining. My name is Aaron Kinnett, as Chris said. I'm a technical specialist working with Autodesk out of the Windsor, Ontario office. Today's presentation is live, so if there are any issues with audio or any of the visual that you're seeing, please enter into the chat window so Chris can let me know. We don't want you guys missing any of the presentation and us talking to thin air. So our presentation today circles around driving industrial robots with PowerMill. And some of the demonstration points we're going to look at today to review is the toolpaths that we're looking at today are all generated in PowerMill itself. We'll look at some operations for milling, trimming, rotary table, and transition options. We'll see how we have full collision detection of the robot components and the machine part. We look at setting access priorities and limit controls to avoid singularities on the robot. And we'll analyze the robot's behavior and movements throughout the operation just to show that we have complete control of the tool orientation around the workpiece. So we'll move into PowerMill. So here we have PowerMill 2021 loaded. For those of you not seen it before, just alluding to what Chris said earlier, the PowerMill robot interface is built on PowerMill. So you're using the same toolpaths you would to run a CNC milling machine. We're just simply simulating in order to get the G code for a robot. With PowerMill running a CNC machine, you don't have to simulate just to get the code. With a robot, you must, otherwise you won't get all the joint angles. We'll look at some of that information as we go through. So different to PowerMill, in its base form for CNC milling machines, we've loaded up the PowerMill robot plugin. So we've got a robot library here of all the commonly used manufactured robots in industry today, whether it be ABB, Kamau, Kawasaki, KUKA, and so on. And we can put your robot in this list as well. If you've got a custom one, we can design it. We just need the CAD file for it. For today's demonstration, we're going to load an Autodesk robot. And we'll look at some of the controls. So in our robot cell pane, this is where we can set up different operations for the validation we want for the robot itself. In the robot configuration, we can look at the robot we've chosen, the dimensions that are mapped out for all the joint angles, the home position we've set, a tool database if we've got any loaded into the database itself, and we pick our post processor. All these changes can be saved as a default once you're sorted out. Looking down the list here, we've got some collision checking options, a little bit different than the standard PowerMill. You can turn on the collision checking, looking through machine tool clearances, holder clearances. You can stop simulation for safety reasons, if you have a certain issue or an access limit's reached. And there's operations in here to look at the virtual teach pendant. So if you're used to running a robot manually in a jog type mode, this is similar to that pendant that you have in your hand. So we give you the option to do that as well. Moving on to the next pane, this is the pane where all the magic happens, and we simulate the robot itself. So if we activate our first toolpath, zoom in here, we've just got a toolpath created on the screen, milling out this pocket area. So we attach to start and we play through the program. The robot's recording all the joint angles at this time to validate the positions. This is the main difference, as I was saying before, between the CNC side and the robot side. If we don't simulate this, we can't record all the joint angles of that robot in order to understand its position, since there's many more solutions with the robot versus a 3 to 5 axis CNC milling machine. So once we're happy with the position, we can just save it. If we go down to the lower pane here, the robot program, I'll just write the NC program so you can see the difference quickly as an example. We open up our header file. It gives us the name and date. The information here can be modified to suit your needs. Each robot requires different types of information. In this case, the header file is listed as a call program. We load the tool information, the spindle speed, the base frame, and then the toolpath that's going to run next. And then if we open up the toolpath, it looks much different than the G-code you'd see for a CNC milling machine. You're seeing here the joint angles of all the rotary axes on that robot and the positions they're at in each location. So again, quite a bit different than a CNC machine. We'll close that for a moment and go back to our robot control pane for a second, just to describe some of the other features. In here, we've got all the options for each individual axis. They're labeled, axis 1 through 6 on the robot, and our end effector today is a spindle for milling, for metal removal or material removal. Each axis can have a priority set to it, whether it be low, medium, high, automatic, or static. This gives you a choice to prioritize certain axes over others in order to, in some cases, avoid singularities. For those of you that aren't familiar with some robot terms, we'll discuss those a little bit more as we go, but singularity is an issue where you have one or more axes that line up with each other. Like in this case, if the 4th and 5th axis line up, that's a risk singularity, and the robot won't understand what to do. So we do have options to get around that, be it these axis priorities, or you can use an automatic singularity avoidance. On the right-hand side here, we have the limits. The machine tool definition file that's brought into the session currently has these limits imported from the text file that we create on the back end. If you wanted to adjust these on the fly, you can adjust the values as a temporary measure to limit that axis from going to a certain position. Perhaps you're trying to avoid another fixture on a position on the rail that you're using, different types of applications for machining. This gives you that choice to limit that axis, and it'll force it to use a different one. Again, more flexibility with a robot than you have with a CNC machine when it comes to choices of reach and how you get to a position. So we'll move on to our next toolpath. This one here is just a pocket playing on the side of the part. If we watch it play through, our 4th and 5th axis do get close to a singularity, even though it's not all the way there, it gets close. So we can look at ways to adjust it so that we can position it the way we choose in a certain location. So if we go to our moves tab at the bottom here, we can just jog that robot around. And this lets you position the robot in any way you choose. And then we can tell it, we've got, in this case, we've got a vector set to free. We can set it to an orientation vector, or we can set it to, in this case, the control vector that we're on at this point in time. So if I set it to that vector, reposition, it'll replay at that position. So you get the control quickly and easily how you want that robot positioned before you run it. So when you simulate here, this is what you're going to see on your robot, apples to apples. So we'll save that one. Here we've got a toolpath that goes around the outside, trimming the perimeter of the part itself. So again, when we simulate this one, we'll see how it behaves. You'll notice as it comes around the outside, you have a lot of extreme movement on the robot. Try to limit the amount of movement if possible so that it's more rigid and runs through the toolpath in a completely smooth manner. A couple different options we could look at here. Instead of using the free choice, we could set it to an orientation vector. But if we look at our toolpath, this one wasn't created with the vectors. So we can just add that in. As always with PowerMill, quick and easy to recalculate or edit options outside of toolpath calculation. In this case, we're just going to turn on the orientation vectors and set them to a value of 0 so that we lock our x-axis. So drawing them here, we can see that all of our vectors point in the x-axis direction. And if we simulate, you'll see how that spindle's locked to that x-axis direction. Unfortunately, we've come up with an issue. PowerMill tells us we cannot reach this location because we had a collision with the machine against itself. So the spindle's collided with the actual arm of the robot. Again, making sure that we solve all the problems in PowerMill before we get to the machine tool and run it, or the robot in this case. So now we've got to address this issue because I do want to keep it in that position for the rest of the toolpath, but if I can't for here, I'll adjust it in this sense. So again, we can just jog this around a little bit and click it out of the way. And then I'll open up my virtual teach pendant. I'm just going to position it to a location where I can adjust where I want to be. This does not have to be perfect. We're not homing in on a position where it has to be exactly where we want it to be. It's just going to be close so that we orientate the position of the robot over a certain distance. By that I mean, I had an issue when I ran through this lower area here. So I want to be able to smooth out the transition of that robot as it positions itself from A to B. So what we can do is go into the orientation vector tab and we can set it to a local point and we can smooth that transition out 300 millimeters before it gets to this point. So way back here, and 300 millimeters after, which is way over here. Again, we'll reposition the robot and we'll play it through with this new position. So we can see everything went through there, no issues, everything's behaving properly. So we can save our simulation. And we had a lot less movement on that one. Another tab inside the robot plugin, we've got the vertical plugin that shows all the control that we spoke about so far. And on the bottom, we have the horizontal plugin. This is the simulation analysis plugin. So if we look here, once you've saved your simulation, if you open up old projects, you can recall simulations. You don't have to verify them by simulating again. You can run it through the simulation here to see the position of the robot at any given point. And it tells you if there's any wrist singularities, elbow singularities, alignments, axis limits, or collisions reached. So you have verification that everything's going to run properly. So when you run this on the robot, it's going to be what you see here in PowerMill. So if we go back into our robot control program again, I'll just add my last simulations here for my side pocket. The simple profile, and then you can see the three toolpaths here that are going to run. If we drag our slider bar across, it indicates exactly where they switch, how they behave, and if there's going to be any issues. We have no issues, so I'm happy with writing that program out to the machine. And again, our folder opens up. We've got the initial header file. We have our start position, and we have our three toolpaths that we're going to run here. Each one's identified here below. You can open up each one of them and verify the joint angles if you wanted to see where it's at any given time. So quick and easy. Another option before we leave this project, we can also adjust the control, like I said before, of these priorities. In this case, we weren't using the rotary table. If we wanted to, we can just set that rotary table itself to a position of high on the list. And if we reattach, you'll now see that that rotary table comes into play and it's able to be used as well. So just another choice on the flexibility of how you can manipulate the robot and how it behaves. The choices are fairly endless in most cases, so that when you use this robot interface, you're not stuck minimizing the ability to control the robot. Everything should be able to be done here so that when you go out to the machine and run it, it's number one, safe, and two, accurate. So we're going to move into another project now. So instead of using a milling head, this time we're going to use a knife to cut through an area and look at just how that behaves. Again, we'll bring in an Autodesk robot. And as I said, this one won't have an end effector of a spindle. It's actually just got a cutting knife that's going to cut through this type of material that we're using. So we'll attach it, and if we simulate the program, I'm just going to save it so you guys can see exactly what's happening. So if we look closely at the simulation, we bring it down here, as we rotate around, we'll notice that the knife's actually violating the part. It's not orientated the right way. So that's not going to give us the result we want. We're not going to have the proper part cut. So again, fixing the issue here before we get to the other end. So what we can do is set the option to an orientation vector of follow. We can restart and resimulate that toolpath. So now if we zoom in, we'll see that we're following along the edge as we're supposed to properly, except again, we're 90 degrees out to what we want to be. So to fix that, it's just a simple angle change. You can enter in a 90-degree value here. And now you'll see that it transitions through that area as it's supposed to, following the cut. Again, you could have made all these changes at once. The reason we're walking you through these is so you see them individually, one by one, so you understand exactly how it behaves and it works, and as it cuts through the material, what it's going to give us as an end result. So just another way that you can use a different type of end effector to do a machining operation or a trimming operation. Lastly, we're going to move into another third project to look at some options for machining again, but it's this time we'll be looking at some transition moves that we're going to have roll through and see how they behave. So initially we've got this car body with a robot on a linear track that we haven't seen yet today. So that lets us utilize both sides of the rail also. And the rail gives us that transition point where we can manipulate it and move it down for different applications, whether it be for reach of a part or just for rigidity on the robot itself. So we'll let this first one play through. There's also an option to play this very quickly if you choose to, just showing the simulation and how it behaves with the robot for those who haven't seen it today before. So again, checking our simulation plugin before we move on, we've got no singularities, no axis limits reached, and no collisions. So we're happy there. So we'll move on to our front light cluster. And we'll play that one.
Hey, Aaron.
Yes.
While that's simulating through, quick question. What
Sure.
are some of the advantages of, a robot over a mill? Like, why would we want to use a robot over a mill?
So again, kind of what I alluded to a little bit earlier, with a robot, you have much more availability of reach, essentially. So
Right.
it has a linear track. You can manipulate it to run on both sides. You can have a part sitting on either side. It gives you more options for control of the axes themselves because you've got a variety anywhere they are to locate them. The only downside is they're not as strong as a CNC milling machine. The robot is stronger when it's closest to its base. In this case, we can see it's fully extended, so it wouldn't be as strong here. It definitely has a little less rigidity and repeatability. So it depends on the end result you need and the accuracy you're looking for. But a robot is a fast growing option in the CNC industry, as opposed to 20 years ago, you just seen them in automotive assembly plants doing welding applications and pick and place operations. Now we see them in a variety of manufacturing for metal removal, trimming, water jetting, laser cladding, and more recently, an additive. PowerMill also has an option for PowerMill additive so that you can add material and remove it as well with a robot or a CNC milling machine.
Beautiful. Actually, there's a question that came in about that exact subject, so we'll save that again for the end, but we'll address that later. Thanks, Aaron. Carry on. Thanks.
You're welcome. Appreciate it. So if we look here, we've completely hit that limit. There's a machine limit that we're hitting. We can't reach the location we're at. And if we had the previous two robots that we had on the screen without a linear track, we'd be kind of in trouble. We wouldn't be able to reach that location. We'd have to possibly move the part. But with this, we have the linear track, so we can take advantage of it. So I'm just going to bring that one back to the home position, and I'm going to jog it down the track. And you can even enter a value. You don't have to always just use the slider bar. So I'm going to place it here. And then from there, we can simulate that again and avoid that axis limit issue. So we'll save this to check our simulation. And while we had no issues with the collisions this time or axis limits reached, we do see we've got a risk singularity here. And if I look at the first one, you can see it. And then the second one right here, it's when this fifth and fourth axis begin to line up. The robot doesn't know which solution to pick, so it can't continue. We could use the automatic avoidance, or we can adjust it ourselves to what we choose, so we don't have the problem. So we can just jog it around a little bit and it avoids that problem. So as long as you nudge it away, like this position here approximately, it doesn't have to be a specific position. There's no art to this completely. As you run them, you get to understand how to avoid the singularities as well, and you can pre-position prior. Again, just trying to show you all the information that PowerMill has so that it can stop any problems from happening, as well as how it addresses those if you happen to miss it, like in this case. So we'll re-simulate that in that position. And now we can see we've removed those risk singularities, so we don't have the problem anymore. So we're ready to run this on the machine. So what we're going to do now is we're going to go and create that robot program. So we've got the two programs here. I won't make you watch the entire simulation, but if we use the slider bar, again, there's an intended issue to happen here. If we bring through the simulation and we transition to the next toolpath, so we're going from the rear window to the front light cluster. If I play it slowly here, so you're going to see that collision right there. We've hit a problem. So if we look at the display issues, again, we've hit that model through this point here. So our transition going from program 1 to 2 is causing a problem. So we need to fix that. So we can do that with a transition move. Again, another handy tool to use in the software to avoid any issues. So we'll just home our robot. And we're going to create that transition move now. This is simply done by where the position of the robot is currently. So I can add my current position here. And then I can make a secondary one if I choose. So I need to bring this down here a little bit so I don't have a problem with where it's going to collide. I can add that one in. And then I'm just going to manipulate my axes here. We can add that position. This is just going to guide, and you'll see in a moment how it helps. So we go into our robot program and we can add, instead of a toolpath, we're going to add a transition now. So that loads those 3 points in that we just picked, and we can just drag them up into the location up at the top here. So now we're in between those locations. If I bring the robot over to this location now, we'll play it. You can see that transition move with the blue line here. That got us around the issue. And this is exactly what happens on the robot. So these transition moves are completely up to the user on how to program them, but it gives you that guidance and the control on to get over and under certain things. So you could have a different type of fixture holding this part down, or you could have an obstacle in the way that may not be modeled in. but it allows you the control you need to safely run your robot and cut your part accurately without damaging anything. So if we just write out that NC program, taking a look at the header file itself, we've got the robot program that's playing, the transition that comes in, and then the front light cluster afterwards. And that transition shows all 3 points that we entered. Again, just another way to give you the functionality you need in order to save the robot in a safe position and then run it on the machine tool. So just in a quick recap today, everyone, we looked at the toolpath generation of PowerMill, and the toolpaths that we're using are the ones that have been in PowerMill for the last 30 plus years. So they're safe, robust, and we're just running them on a robot instead of a milling machine. We looked at different operations from milling to trimming with rotary table and transitions. We looked at how we can fully collision check the robot's components and prioritize the axes, and looking at issues that could entail like limit controls with the axes, as well as avoiding singularities. And we've seen how we can analyze the robot's behavior to make sure that we get the most out of it based on the user input. So we'd like to look at some questions now, Chris, if we have any. So I'll just stop sharing.
Yeah, Aaron. Did get some questions generated here, a few good ones. We'll start with the obvious one. I think that I think you kind of already answered this, but I'll throw it back out there just in case. But can we add a welding head or metal deposit head onto a robot and create additive toolpaths? For
sure. So one of the common uses is the subtractive head, like I showed there with the milling head or the knife. We also can do a laser welding or an arc type welding cladding head. We also do water jet as well.
Perfect. Any benefit from one manufacturer to the other? Which one basically is better with the software?
I would say it depends on the application. You talk to a lot of different people that run different robots, and they like them for certain things, you know, where you have your ABB and Motoman, we're more in the automotive industry, and you have KUKA for repeatability and accuracy is quite high on the list of customers using them for milling applications, as well as direct energy deposition, like the DED stuff for additive.
Right.
It just depends. We work with all the manufacturers. So
okay. Go ahead and hide that question. What version of PowerMill do I need for robot?
In order to run this, recently they've changed the structure of how PowerMill sold. There used to be a standard, premium, and ultimate, and it came in the premium package. Now there's standard and ultimate only, so it's in the ultimate package. So
ultimate, okay.
Standard, you can only run up to 3 axis or 3+2 with a milling machine. With ultimate, you get the full range of the robot, the 5-axis control, and the Bliskin blade module, along with the PowerMill additive that we talked about for the DED heads.
Okay. Last question that we have in this chat right now. I'm not quite sure what the question represents. Maybe whoever wrote this question can elaborate on this, but I'll just throw it out there. Is this manufacturer specific or only robot kinematics matter? So I'm not 100% sure what was being laid out here in this question, but
maybe the person that wrote it can elaborate a little bit.
Yeah, well, while we're talking about kinematics, I saw that you had a robot in the last presentation that was on a rail system.
Yes, sir.
And then you had one that was on a rotary table. Are there any other configurations? Like, what is the maximum configurations you can apply to a PowerMill robot cell?
You can have, it depends on what you want to use. Like you could have a rotary table in the same cell as well as a stationary table and work back and forth in between them.
Mm-hmm.
There are applications we've had even with 2 robots in play, where one's doing a sanding operation potentially, and the other one's doing a polishing operation. There is a lot more integration on this side, and to be fair, Autodesk doesn't do the integration. There's robot integrators that specialize in this. They set the robots up. Autodesk's role with PowerMill is to simply drive these robots.
Right.
So
okay.
As long as they're set up to run the application that the customer requires, we can create the toolpaths, the water jetting, the additive programs, the welding toolpaths, but we don't do the integration side.
Right, makes sense. what about end effectors? I saw that you had a milling, a cutting, laser, anything else besides polishing, and was that pretty much cover them all?
I said, well, you got different options too. Like I said, whether there's what we had today was robot had the end effector on it, but sometimes there's what they call part on robot. And so instead of us having a stationary part and machining it, the sanding operation would be one where you could have the part attached to the end effector of the robot, and you bring it up to a rotating sanding drum.
Okay.
We had a customer that was making chairs, and they were sanding the legs manually. So this was an operation where they could sand that quite quickly in a production type atmosphere for the chair. And it was something where it was repeatable as opposed to a handheld tool where there's just no
gotcha.
amount. So.
Okay. While we're talking about it, I know the question wasn't asked, but what about tolerances and accuracy with robots? There's obviously got to be a give and play between a robot and a milling machine.
There is. You're only going to expect a certain amount of accuracy of the robot, and you've got to be cognizant of that. And there is repeatability issues with certain ones, and it depends on how you're pushing it.
Right.
Robot's not made to put in a 2-inch cutter and fly cut a steel material. If you're using heavy foam, like a 10-pound foam, or if you're using Ren board or fiberglass, maybe cutting aluminum.
Right.
You can cut steel with them. It's just they're not as rigid as the milling machine in that case. So as long as you're using it within reason, the biggest thing is accuracy and repeatability. You need to be able to repeat that process over and over to make the robot produce the same operations. And a lot of that comes with the integration. So the integrator that sets up the robot can change the parameters behind the scenes. So it's kind of a loaded question because there's not a one size fits all.
Right. Okay. I don't see any other questions here. So if you're satisfied, what we'll do is we'll kind of just maybe wait a couple of minutes here and see if there's any other questions. Feel free to put them in, everyone. We only have Aaron for a little bit of time, so we want to maximize, his expertise here while he's on the call. So.
Yeah, I hope everybody got something out of it today, because for me, in my background, I was a machinist in a mold shop in Windsor and Chris has a similar background, so didn't have any exposure to robots at all when it comes to welding. I just thought they were used in the automotive industry to weld things. We never seen them for anything from, whether we use it today for architecture, for a lot of different things. People use it for statues, for applications where it's not safe to be in an area with certain compounds and certain chemicals. If you're doing like a sand cast mold, they put a sleeve over the robot and allow that to remove the material so that the person's not in harm's way.
I gotcha. All right. Yeah, it looks like no other questions. We did get a comment that the presentation was awesome. So
cool.
Good job, Aaron.
Thanks, Chris, for having us. And we really appreciate the opportunity to work for this expo. Everyone enjoyed it today.